All right, we're going to get started. I recorded on Friday, and it was just a bad setup. I got glitches of video, and it wasn't very good. So I know that we missed the video on the Fundamental Theorem of Calculus, Part 1. Okay, so just to recap, we're in Lesson 5.4. This is the Fundamental Theorem of Calculus, which makes it seem kind of important. The Fundamental Theorem of Calculus. Yeah. So part 1 of the Fundamental Theorem basically walks you through this idea that inverses are derivatives and integrals. I said that so badly. Integrals are inverses of derivatives. Okay? Yeah. What just happened? I think I just undid everything that I had on paper.
This is again.
Yeah.
For the people in the back.
For the people in the back. Okay. So the idea here is that if I take the derivative of the integral, I'm left with the function. They undo each other. Okay?
What did you get?
So what do you get out of doing that? Well, let's say that I have this idea that potential energy is equal to the negative integral of force. Right? That's coming straight out of our physics lesson that we just did. How do I find potential energy given a force? Well, I'm going to integrate the force. But what if I'm given a potential energy and I know this relationship? Then what could I do to find force? So given force, I'm going to integrate to get potential. But what if I am given potential? How do I get the force? Take the derivative. Because the derivative of the integral is the function. Okay? So it works both ways. If I say x plus 2 equals y, the inverse of that is going to be y minus 2. Okay. So they work in opposition to one another. They're opposite operations almost. So like addition, subtraction, division, multiplication. If I have a square root, how do I get rid of it? Square it. If I have an integral, how do I get rid of it? Take the derivative. Okay. Is that making sense to you guys? Is that much more clear today than it was the other day? Maybe? Okay. So then we looked at a couple of examples. Example 3, and I don't want to work all of these, but maybe it's helpful to work one. Example 2, it has find the derivative of each function. And so we're looking at A, where g of x is the integral on 0 to x of this function, the square root of 1 plus t squared dt. And it wants the derivative in terms of x. So I look at my limits of integration here, and the derivative of the integral is going to be the function in terms of x. So g prime of x here is going to be the square root of 1 plus x squared. And I'm able to just take the function. And instead of it being in terms of t, it's now in terms of x because I was looking for the derivative in terms of x. Does that feel a little better? The derivative of the function, or of the integral, is the function. Okay. And then there were some in your homework. Did you have to do the u sub anywhere? Yeah. So, for instance, number 17. Number 17 of your homework. You're given h of x is the integral on 1 to e to the x of natural log t dt. And it wants us to find h prime, the derivative in terms of x. So it looks like I would just take the derivative and plug in that e to the x business, right? The problem is this e to the x up here is not x. So what we have to do is we have to use a letter, u, And we're going to swap that out and rewrite our integration statement here. Okay, so h prime of x is going to be the integral on 1 to u of natural log t dt. H prime of x is going to be d dx, the derivative in terms of x on 1 to u of natural log t dt. The problem is this is the derivative in terms of x, and I've now put in here u. So in order to undo the u business, then I have to also multiply by the derivative of u in terms of x. And that allows us to be everything in terms of x. Does that make sense? And I'm actually taking, since in front here I have d dx, this actually needs to say d du, because I have taken out the x here and I put in a u. So I want to take the derivative of the integral in terms of u, which when I do that is going to leave me natural log u. I take the function in terms of u. Multiply that by du dx, which, what is du dx? If u equals e to the x, then the derivative of that in terms of x is also e to the x. And so I'm going to have times du dx here, in nice and purple, times du dx. When I simplify that, that's going to be the natural log of u, which was e to the x, times du dx, which is also e to the x. And here would be your final answer for number 17. That's almost your final answer. What's the natural log of e to the x?
1 over x.
That's the derivative of the natural log. Just x, right? Natural log of e to the x is just x. So your final answer here is x e to the x. This is number 17 from your homework. So this is a little chain rule. Okay? Really, the rule here is if you take anything but x in your upper boundary, your upper limit, then you're going to have to multiply in the end by the derivative of that thing. It's a chain. Okay? This should all catch you up from what you missed on Friday. The derivative of the integral is the function in terms of x. So unless otherwise stated, that's all. If you have an upper boundary that's not x, you're going to end up multiplying by the derivative of that thing. Everybody okay here? Any questions on this? Drake, we miss you. Come back. Okay, so here's our next section. And to begin the next section, we start looking at the second part of the fundamental theorem of calculus. Okay, this is called the fundamental theorem of calculus part 2. It says we evaluated several different or definite integrals using the definition involving Riemann sums. This process can be long and tedious, and you've felt that. It's hard to go in and chunk pieces of formula and add all of those up. The second part of the fundamental theorem of calculus provides a much simpler method for evaluation of definite integrals. It says this: if f is continuous on a to b, then the integral on a to b of f of x dx is equal to the antiderivative at b minus the antiderivative at a. And we've kind of dabbled in this in physics. I'm hoping that after this section of this lesson, we can make that flawless. Okay? This is really where it all comes together. So we will abbreviate this theorem as FTC2, which whether we use that again ever or not is kind of, I don't care. But here's the deal. The theorem says that the value of the integral of f of x dx on a to b can be obtained by finding an antiderivative of f, then subtracting in the proper order. Okay, this matters. We always do b minus a, big minus little, because those boundaries a to b on an interval are always listed from least to greatest. So we always want to do f of b minus f of a. Remember that this integral is equal to the negative integral from b to a. So in the event that we flipped it, we're going to get an opposite sign. So we always want to make sure that we're subtracting antiderivative of the big one minus antiderivative of the little one. Is that making sense to you guys? Okay. The values at the endpoints of a and b. All right, so that brings us to this page. I just thought that these pages in this textbook were making a lot of sense to me. What page are we actually on? 434, 430, 437. I skipped the proof. Oh, I skipped the proof. Yeah, this looks like at the bottom on 438. This is the top of page 438. Okay, so what was interesting is it says this works for an antiderivative. I know that I read that part to you. An antiderivative of f. Okay, how many antiderivatives are there possible? An infinite number amount, because they differ by that constant c. Have y'all seen that before? Where we found an antiderivative and we graphed it, and we found a different one at a different c value and we graphed it, and they're all parallel. They all have the same function, but they differ by that arbitrary constant. Well, since we get to use an antiderivative, it's best to not have the c. Because one of those antiderivatives could be c equals 0, right? So since we get to use an antiderivative, then we just drop the plus c part here. This is on a definite integral. We'll drop the plus c. The reason that that is allowed is because if I take the antiderivative, look at this part right here, and I evaluate that on b minus a, and I let that c hang out here, then I've got g of b plus c minus g of a plus c. And what happens when I have that c minus c? It cancels anyway. It cancels anyway. So the antiderivative that is the easiest to use and is going to be the most available to you is going to be the not plus c part. Okay, just let it be. Any questions on that? Okay, they walk you through a paragraph right here that says the FTC part 2 is certainly reasonable if we interpret it in terms of physics. If v of t is the velocity of an object and s of t is its position at time t, then v of t is s prime of t, right? Velocity is the derivative of the position. So s is an antiderivative of f. If we consider an object that always moves in the positive direction, then we could guess that the area under the velocity curve is equal to the distance traveled. It's equal to the distance under the velocity curve. Does that make sense? Are you seeing this formula? The integral of v of t, the integral of velocity, is equal to the distance traveled at point B minus the distance traveled at point A. Everybody good with that? Yeah, okay. I think y'all are sleeping and ready to work problems. I don't blame you. I don't blame you. All right, so here's example 5. Example 5, it says evaluate the definite integral of, on the interval from 1 to 3, of e to the x dx. Okay. And so our rule here is it's going to be the antiderivative evaluated on 1 to 3. Okay, so from 1 to 3 of e to the x dx is equal to, what is the antiderivative of e to the x? E to the x, right? The derivative of e to the x is e to the x, which means its antiderivative is also e to the x. So this answer is going to be e to the x evaluated on the interval from 1 to 3. And we use this big square bracket business. I have also seen this notation where you put the whole function that you're interested in the square brackets. I kind of prefer that because it lets me know, hey, I'm not done yet. I've still got to go in here and plug in these b and a values. Okay? I've also vertical line here where I would have e to the x with a vertical line and then 1 to 3. I've seen that too. I don't use that one. I prefer the square brackets because they help me remember what I'm supposed to do here. Okay? So now to finish, we're going to evaluate e to the x at e to the third power minus e to the first power. And you plug in your b term, and then you subtract, and you plug in your a term. If there are more than one term in your antiderivative, it's important that you need to open parentheses here because you'll be subtracting everything in this term. And if you don't open parentheses, you'll miss it. Okay. So final answer here is going to be e cubed minus e. E cubed minus e.
Those are just two real numbers, right?
Those are two real numbers. So I suppose if you had a calculator, you could go in there and figure out what those numbers are.
The book does not do that.
The book does not do that. So neither shall we. Okay, here comes example 7. Example 6. I lied. Example 6, it says, find the area of the region R bounded above by the graph of y equals x squared, below by the x-axis, and lying between the lines 0, x equals 0, and x equals 1. So what region are we talking about here? We're looking at a parabola, y equals x squared, on the interval from x equals 0 to x equals 1. And we're talking about the area bounded above by the graph of x squared and below by the x-axis. So it feels like we're looking at this little triangular looking whoopee. Yeah? Okay, so write it out. What are we doing here? We are saying I want to take the integral on the boundaries from what to what?
0 to 1.
From 0 to 1 of f of x, which is x squared dx. And that is going to equal the antiderivative of x squared, which is x cubed over 3. And remember, we're not interested in the plus c part. That happens when we're dealing with indefinite integrals. At this point, we have limits of integration, and so it's not indefinite. And now we evaluate. We are going to have 1 cubed over 3 minus, and you could get in the habit of that open parentheses right there. It's not exactly necessary because there's only one term. Note that a lot of times if x is 0, that part will do something. A lot of times it goes away. Okay. So what's my answer? 1/3. So what does that tell me? What do we find? We found the area of that not pretty geometric shape. That's not a triangle. Thank you, calculus. Do you understand? Okay? Up until now, you've given shapes like triangles or circles or semicircles or trapezoids. And we've been able to calculate the area under the curve because they were geometry things, right? This is a not geometry thingy. This is something that looks to be cut by a function. It's special. It's neat. Appreciate. Ooh, ah. Wow. Thank you. Now we're on the right page. Wow. Okay, here's example 7. Remembering common antiderivatives. Brooks, wake up. This is going to be special for you. This is example 7. Remembering common antiderivatives. Okay, so we're evaluating from 3 to 6, the integral of dx over x. And this will really hurt your heart if you can't see that this is equal to the integral from 3 to 6 of 1 over x dx. Okay? That dx over x looks confusing as all get out. And I've seen kids miss on mock exam on the AP test because they won't see this for what it actually means. All right. So what is the antiderivative of 1 over x? Natural log. Natural log x, right. So this is a common antiderivative, and they're telling you, remember those things. The derivative of natural log is 1 over x. So the antiderivative of 1 over x is the natural log of x. So this is going to equals natural log x evaluated on the interval from 3 to 6. Okay. So we're looking at natural log of 6 minus natural log 3. Reach back in your archives. What are the rules when I'm subtracting natural logs?
You subtract 6 minus 6.
Not subtract 6 and 3. Divide. Good, Thomas. See, I have been missing you. Divide your arguments. 6 over 3 is going to be natural log 2. Good. Good? Any questions on this one? No? Are we finally feeling like, okay, now we can work with this? This is trucking along. I think we've been in baby steps kind of since Christmas where we're like, just get to the point. Do the thing. All right, here comes example 8. It says, find the area of the region R bounded by the graph of y equals cosine x below the x-axis. What? Below the x-axis and lying between the lines x equals 0 and x equals b, where 0 is less than or equal to b is less than or equal to pi over 2. Okay, so what the world is this even asking us to do?
It wants only below the x-axis, right? So we can do intervals of where cosine is negative?
We could. It wants the area below the x-axis and lying between the lines x equals 0 and x equals b. Here's what I think. I think we should look at cosine as a picture. And we're only going to pi over 2. Okay, so unit circle wise, we're only including from here to here, this arc.
Never negative there.
So what is cosine of 0? Cosine of 0, that's your x value at 0. 1. Okay, so cosine of 0 is 1. That's going to start up here. And what is cosine of pi over 2?
Oh yeah, it's 90.
And then it would go like this. Do you agree with that? We are interested in the area under this curve. Okay. Bounded above by the graph of y equals x, or cosine x, and below by the x-axis. So the upper boundary is this y equals cosine x. The lower boundary is this x-axis.
I thought it said at 1 below the x-axis.
Right. So that's kind of a reading thing. And then lying between 0 and pi over 2. And we want to find the area of the region. And it says lying actually between 0 and b, where b is any value between 0 and pi over 2. So any value from 0 to b, we want to write the integral statement for. We don't know what b is. So this is going to be the integral on 0 to b of cosine x dx. What is the antiderivative of cosine? Sine. Good. So we're going to evaluate sine x on the interval from 0 to b. So we'll have what?
Sine of b, and then minus sine of 0.
And what is sine of 0 degrees? That's going to be here. Sine of 0 degrees is 0. So this can go away. And our answer is sine of b.
Do we define that, or is that just a...
We don't know. B is a fluctuating number between 0 and pi over 2. Everybody good with this one? Okay. This was that picture. Everybody see it? Okay. One last one. This is example 9. It says, what's incorrect with the following calculation? What's wrong with that? So they allowed this 1 over x squared business. This is the function, 1 over x squared. They allowed this function here to be x to the negative 2. Seems like that's the direction they went. And then they found its antiderivative to be x to the negative 1 over negative 1. So they added and they divided by the new thing. It gets really twisty when you're going back and forth between derivatives and integrals. In my last year physics class, we decided to say derivative, drop, subtract. It's kind of our mantra, derivative, drop, subtract. And for integrals, we said integrate, add, divide. Okay, that kind of came in handy when we were like, what do I do? Because you get real twisted up. Okay, so derivative, drop your exponent, subtract. Integrate, add 1 to your power, and divide. So it feels like that's what they did. They took that negative 2, they added 1 to it, they got negative 1, they divided by the new thing, then they evaluated on negative 1 to 3. So they did plug in their 3, then they plugged in their 1. So far, there's not a problem here. Are you following this? The issue is, if you were to graph y equals 1 over x squared, anybody off the top of your head know what this looks like?
Please pardon for the interruption. Teachers, please release these students at this time. Crystal Gonzalez, McKinley Daniels, Aubrey Lindley, Stacy Mello, Autumn Chaplow, Jocelyn Perez, Brooklyn Perez, Reagan Jewett, Lauren Richardson, and Sophie Davila. Please release those students at this time. Thank you.
Okay, so this is the volcano function. This is the volcano function. Well, what did they find for the area under this curve? A negative number. What is the area under this curve from negative 1 to 3? Should be positive at least because it's above the x-axis. But also, where do I stop? The area is infinite. This is not continuous. This is not a continuous function on this particular interval. From negative 1 to 3, this has an asymptote at 0. So you can't find the integral of a function that is discontinuous.
That was one of the rules.
On that interval. Now, could I, Cohen's very excited. Could I have found the area under the curve from 1 to 3? Sure. But it's got to be continuous on the interval. Otherwise, you're kind of out of luck. Yeah, so you got to remember, I mean, they didn't do anything wrong, but they got a negative number on a function that is totally above the x-axis. So that should be like red flag, something bad happened here.
It went so high, it wrapped back around.
It wrapped back around. They dug to China and back, right? Yeah. Something like that. So understand that has to be, it's got to be continuous on the interval, or you don't do this. Okay. One last piece of information for you. Nope, that's all I took pictures of. Look with me on page 440. They kind of tied it up in a really nice little bow. And I'm kind of very sad I didn't take a picture of that. It says this is a fundamental theorem of calculus. And it has part 1. The derivative of the integral is the function. And it has part 2. The integral of the function is equal to the antiderivative at b minus the antiderivative at a. And we have used that in physics, but now hopefully you understand why and what we're doing.
It even says suppose f is continuous.
Suppose f is continuous. Hey, we've got a restriction. Suppose f is continuous on that interval. Doesn't mean that I can't integrate a discontinuous function on a different interval, but on the interval from a to b, it's got to be continuous. Are we good here? Any questions? Okay, that's the last of this unit. So tomorrow will be a review day, and then on Wednesday we'll test over sections F 1, 2, 3, and 4. Okay? If you're not doing your homework, you should be. Get that homework going on your orange paper. Deal? Okay.